Hello, my name is Giovani Guizzo. I'm a research fellow at University College London, and today I'm going to present to you the paper Cost Measures Matter for Mutation Testing Study Validity. This is a paper I wrote with Professor Federica Sarro and Professor Mark Harman, both from our group Solar. If you're watching this presentation, then you might already know about mutation testing, but I'll start with a quick overview on this topic, just to recap. Basically, you have your original program, you apply mutation operators that syntactically change the code, and then you generate a mutant, which is a buggy version of your software. Well, the objective of mutation testing is to create a test suite that can kill those mutants. To kill a mutant, one must first execute the test cases against the original program, and then against the mutant program. If the output of both are different, then the mutant is said to be killed. Well, usually, the more mutants you kill, the higher your mutation score. So you have to create test suites that can try to kill all mutants. The greater your mutation score, the better your test suite is in revealing the faults represented by those mutants. However, running potentially thousands of mutants against multiple test cases incurs a great cost that still hinders the adoption of mutation testing in practice. There are two main types of costs in mutation analysis. The manual cost of assessing the equivalence of the mutants. Basically, an equivalent mutant is a mutant that cannot be killed by any test input that can be created. So, this mutant equivalence is done manually. And the second type is the computational cost, which refers to executing the mutants against the test cases and the execution time and the resources spent to kill those mutants. So in this paper, we're going to focus on the computational cost of mutants. Okay. So, well, the computational cost of mutation testing is still a big issue. So in order to reduce this cost, researchers have proposed to use a strategy called Mutant Reduction. So a mutant reduction strategy selects fewer mutants from the set of all mutants, because fewer mutants means less execution cost. However, many papers fall into the wrong assumption that by reducing X% the number of mutants, the execution cost is also reduced by X%. In fact, this idea is so commonly disseminated that the number of mutants has become the most used cost measure in the mutant reduction literature. The problem here is that different mutants have different costs. So we cannot expect a ratio of 1-to-1 between mutants and between number of mutants and the true execution cost of mutation analysis. So this is a threat to validity that can lead to misleading conclusions about which strategy will be more effective on reducing the cost of mutation analysis. So with that in mind, the objective of this work is to investigate the effects of using and reporting number of mutants rather than the actual execution time as a measure of cost when performing mutant reduction. For this end, we conduct an empirical study to determine differences between the proxy measure of number of mutants and the real execution cost of such mutants, the execution time. Naturally, we first conducted a literature review on mutant reduction by gathering some extra information on this problem. So we found 75 papers in the literature, 60 of which, or 80%, do not measure any execution time at all. What is more concerning is that 54 of those papers, or 72%, use number of mutants as a proxy for cost. Only 6 papers acknowledge that this is a threat, and only 5 papers try to deal with this threat somehow. Hence, the threat investigated in this paper, if it's real, it can affect a large amount of existing literature and the future literature on mutant reduction. In order to do so, in order to evaluate how big this threat is, we conducted an empirical study. In this empirical study, we aim at answering 4 research questions. First, we focus on research question number 1 focuses on the differences, or errors if you will, between the number of mutants and the execution time measures. In research question number 2, we analyze the potential correlations between the observed errors and the properties of the systems under test to try and better understand why those errors occur. Research question number 3 focuses on unveiling whether the rankings of different strategies can change when comparing their costs with both measures. So, can the rankings of the strategies, when comparing them about their cost, can they change? And finally, research question number 4 asks, does it matter? To do so, to answer this question, we aim at reproducing a foundational paper on mutant reduction in the literature and see how the scientific conclusions can be affected by those findings. Okay, to run our experiment, we use PIT, a well-known and powerful tool for mutation testing of Java programs. We also run our experiments on 10 real-world software used in previous work. These programs are of different sizes, test coverage, mutation time, and testing time. So we have a good variety of programs here. So to answer those questions, we use two types of strategies. First, random mutant sampling, or RMS for short, and selective mutation, or SM for short. The former selects mutants at random, and the latter selects fewer operators to generate those mutants. So by selecting fewer mutants, or by selecting fewer operators to generate fewer mutants, we can theoretically reduce theoretically and practically actually reduce the cost of mutation testing. So in order to evaluate those strategies, we execute them for 30 independent runs because they're stochastic. And then finally, it's important to highlight that in this paper, execution time is what we consider the true cost of mutation testing, the true computational cost of mutation testing. And the number of mutants is the proxy or surrogate measure for this cost, which is used in the literature, very commonly used. Okay, now that we have established the experimental setup, let's go to the answers. Research question number 1 first, then we compare the errors between number of mutants and execution time of random mutant sampling selection strategies. Random mutant sampling is arguably the most naive type of mutant reduction because it's unbiased. It doesn't select mutants based on their types. It's done uniformly at random. So it makes sense to use this type of strategy to measure the raw error between those metrics. To do so, we used RMS from percentages from 10% to 90% in steps of 10%. So we have 9 RMS strategies. Then we compare the percentages of sampled mutants to the percentages of execution time needed to run those sampled mutants in relation to all mutants. In this comparison, we use 4 error metrics commonly used in statistics, namely mean sign difference, mean absolute error, mean squared error, and mean absolute percentage error. So without further ado, this is the first result that we found. What you're seeing here is in the highlighted area is the mean sign difference between the execution time percentage and the number of mutants percentage. Positive values mean that the strategy is more expensive than the surrogate measure indicates, and negative values indicate the cheaper strategies. So for instance, if you look in the first cell, you can see that the 10% random mutant sampling strategy selects 10% of mutants. However, the difference between the number of mutants and the true execution time is 24.86 percentage points. It means that the cost of this strategy is 34.86% of the total cost of executing all mutants. As you can see, those values, they vary widely from plus 46 to minus 25. Summarizing these results, though, we can observe that on average, the error is on 44.22%. Or, in other words, the difference between both measures is on average 44% more or less than the real execution time. This is a non-trivial error between those two metrics. And so, in order to better understand how this works, we performed some set of statistical correlations between the properties of the systems under test and the errors found. To do so, we executed the Spearman's correlation coefficient test to find any correlation. We found only 2 statistically significant and large correlations, namely between the mean absolute percentage error and the logical lines of code, and the mean absolute percentage error and the total number of generated mutants for the program. In other words, the bigger the program, or the more mutants the program has, the less reliable the number of mutants is at capturing the true cost of the reduced set of mutants. So, now that we found the error, we want to know if this impacts conclusions of scientific findings. So, for research question number 3, we compare the strategies. Just recapping, we have random mutant sampling and selective mutation. We execute all of them against the 10 programs, and then we compute the execution time and the number of mutants, and then we rank them on the left side by number of mutants from cheapest to more expensive, and with the execution time from cheapest to more expensive. What you're seeing here are the ranks of the strategies, and the changes in ranks are highlighted. And as you can see, only for one program the ranks did not change, only for J-Freeshard. For all the others, there are at least 2 changes in ranks. In fact, 37% of the time the ranks are disrupted, and all the changes are in favor of selective mutation. This means that selective mutation is actually cheaper than the number of mutants measured indicates when compared to random mutant sampling. So if an engineer is to compare those strategies, they're gonna analyze those ranks in number of mutants, and if they analyze the same ranks but now using execution time, they're gonna see that, well, the strategies have different costs. Okay, now that we established that there is a non-trivial error, that this error is larger at scale, that it's worse at scale, and that the ranks of the strategies change, the final question is, does it really matter? So to answer this question, the objective is to assess the impact of those findings on scientific conclusions of previous work. So to answer that, we've reproduced the work of Offutt et al. Published at TOSEM in 1996, called An Experimental Determination of Sufficient Mutant Operators. In this seminal work, the authors compare the effectiveness and cost of 4 selective mutation strategies, namely RS selective, RE selective, ES selective, and E selective, each of which removing a type of mutation operator from the mutation analysis. In their work, they compare the cost of those strategies based on the number of mutants generated by each one. However, in our work, we actually measure the execution time now. We actually get those strategies, we execute them, compute the execution time, and then compare in the same manner. The difference here is that we use 10 real-world programs, the ones that I showed before, and those are Java programs. Anyway, for the results now. So this is the main result of our paper. What you're seeing here are the results of percentages of number of mutants on the left, compared with the percentages of execution time needed to run such mutants on the right. Each line represents a different strategy, and crossing lines represent changes in rank. So if the engineer were to choose the cheapest strategy based on the number of mutants, their choice would be either E-selective or RS selective, each of which generating the fewer mutants for 5 out of 10 programs. So those 2 strategies here, if you look only on the number of mutants, they are tied. However, when using the real execution cost, their conclusions would be unequivocal. RS selective is the cheapest strategy for all 10 programs. Therefore, a key finding relied upon a quarter of a century can be transformed from inconclusive to unequivocal by choosing to use the execution time, true computational cost of those strategies, instead of the surrogate number of mutants. Alright, so after all the results that we found, the takeaway message that we want you to take home now is, when trying to reduce the computational cost of mutation analysis, always report execution time to avoid a potent threat to scientific validity. It sounds simple, but the vast majority of papers in the literature, they do not do that. So, in conclusion, we highlighted the threat of using number of mutants as a surrogate of cost. We showed that a great majority of papers are susceptible to this threat. We measured the magnitude of the error between those metrics. Then we showed that it can change the ranks of the strategies. And finally, we demonstrate how it can affect scientific conclusions by reproducing a foundational work on mutant reduction. My name is Giovani Guizzo. Thank you for watching, and if you have any question, please do not hesitate in contacting me. Cheers.